Don't we love a bit of electrolysis? We are on part number 3, and this one is all about the extraction of aluminium. Now, aluminium is a very, very, very common metal, right? It's used in so many things. It's used for pots, pans, foil, bicycle frames, etc., right? So loads and loads of things. It's very, very useful and in some reasonable demand. However, aluminium is very, very reactive as well. And so, what that means is a few things. Number one, it's ore. It's going to be mixed with a few different compounds, right? Because if it's sitting in the earth, there's lots of things that are surrounding it. And because it's reactive, it's going to join with a few different things. And one of the things it most commonly joins with is oxygen. So it forms a compound called aluminium oxide. So when you find like an aluminium ore in the ground, it's going to look something like this. So you have like this rock, there's a bit of aluminium oxide in there, maybe like 60-70% or something like that. So it's really, really useful. We want it because we want to get that aluminium out of it, but it's also surrounded with a few impurities. So I'll just highlight that in blue. So the other parts of this are impure, and that's basically rubbish that we don't actually want. Okay, so we just want the aluminium oxide from the middle, and then what we're going to do is hopefully do a little bit of chemistry and just get the aluminium out of there and get rid of the oxygen as well. So there we go. Okay, awesome. So that's what we want. However, we've got a little bit of a problem because aluminium is quite reactive, as we said, and it's above carbon in the reactivity series. Now, anything that's above carbon in the reactivity series must be extracted by electrolysis. Anything which is below carbon can just be heated with carbon in essence, right? So we say that it can be reduced by carbon because you basically heat it up with a bit of carbon, and the carbon will react with the oxygen that's mixed in with those metals and leave as carbon dioxide. So great. Now, we've got to use electrolysis. The name of the ore that we use is called bauxite. So that there, right? Handy name. Maybe jot that one down. You might find it useful to pop in your exam or whatever. Now then, remember, this is what I said. We've got this ore over here. We don't want the rubbish that was surrounding it, so the blue bits there. We just want the aluminium oxide because this is what we can take and extract the aluminium out of. So this diagram represents it perfectly. So we've got that there. We want the aluminium, not really the oxygen as such. We just want that there so we can go and make all these pots and pans and whatever we need to make. So to do this, what we're going to do is use electrolysis. And remember that compounds that undergo electrolysis need to be either molten or dissolved in water. We've got a problem. Here's the problem. Aluminium oxide is insoluble in water. And so you're not dissolving it, right? That was one method to get our ions to separate. So we're not going to be able to do that. But the other issue is that we've got to melt it, but it's got an extremely high melting point. So you can see there, massive melting point, over 2000 degrees. So number one, that's going to require so much money in energy costs to heat all that stuff up. Number two, we're going to need lots and lots of special machinery to even get that high anyway, right? You're not going to find ovens reaching that kind of temperature, just down your local shop or something, okay? So it's going to cost a fair bit of money. We need some special machinery to do this. But chemists have found a little way to reduce the temperature at which we can carry out this electrolysis. So we don't need to go up to seriously high temperatures. What we can do is mix aluminium oxide with a different ionic compound, and that's called cryolite. Note that down, okay? And cryolite allows us to carry out this electrolysis at a temperature of around 850 degrees, so far lower than it was before. Now, why is this good? It's obviously far better because it saves us money. It saves us on energy cost, number one, and it's obviously so much better for the environment, right? We're not going to be burning as much fuel to get temperatures of 850 degrees as we were to get thousands of degrees, okay? So much better for the environment. There we go. Now, we've got this aluminium oxide, which is solid, so Al2O3. However, when we then heat it up using cryolite, we're going to separate this and we're going to get it into your Al3 plus ions because aluminium is in group number 3, and you're also going to create O2 minus ions because oxygen is in group number 6. So this is what we will have. we have our electrolysis apparatus here, massive tank that this happens in, and you've got Al3 plus ions and O2 minus ions in there. Now, a few things we should talk about is, obviously this doesn't look like the equipment you'd have in your lab, so we'll talk about this really quickly. The negative electrode, which is your cathode, is made from graphite, but what it does is it actually coats the whole tank that this is taking place in. So that whole thing there, the black line there, is your negative electrode. The positive electrode is kind of suspended into that solution there. And that there, your anode, is made from graphite or carbon. And remember, graphite is really good for this purpose because it's inert, number one, and it can conduct electricity, number two. So that's the two things we need an electrode to do. And then you've got your electrolyte in here, which is your molten aluminium oxide, Al+, and 2- ions are what's in there. What's going to happen? We've got your Al3+ ions. Those are positively charged, those are cations. Where are they going to be attracted to? Well, your cathode, so down here, so to that black outline around the tank over there. Your O2- ions, on the other hand, are going to be attracted to the positive electrodes up here, your anode. And so what we need to do now is look at the reactions that are going to take place. We're going to start by looking at the negative electrode. So you'll have your Al3+ ions. They're in liquid form down here. Now they're going to form aluminium. So aluminium is just Al. And that there is going to be, well, a solid, but at these extremely high temperatures, it's most probably going to be some sort of liquidy substance that's going to settle just towards the bottom. But I'll put it as solid for the time being. Just remember though, at high temperatures like that, it will probably melt and you'll have it lurking around down the bottom here. Now, Al3+, it's got a 3+ charge. What does that mean? It means it's kind of lacking 3 electrons. And so in order to become neutral, what's it got to do? It's got to gain 3 electrons. So like that. So what's happening to the aluminium? It's gaining electrons. So it's being reduced, all right? This is reduction going on over here. So there it is, reduction. Now let's look at what's happening on the other side. So you've got your O2- ions. They're attracted to those positive electrodes. So you'll have O2-. That's also in liquid at the moment. And what's it going to form? Well, those there are going to form oxygen, so O2, which is a gas. But remember again, there's only one oxygen here, 2 on this side. So what do we need? Well, we need 2 of these ions, okay? And each of those oxide ions has a 2- charge, which means it's got 2 electrons too many. So it needs to discard 2 of these electrons or lose 2 electrons. But each of them needs to lose 2. So in total, we need to put 4 electrons on the right-hand side. So there it is. Let's just quickly close that off there. There we go. Okay, great. Now, oxygen, it's going to be given off as a gas. And that gas is going to be around this electrode here, around your positive electrode. Now, we did say that that there is made of graphite, which is carbon. And so, that's what it's going to look like. There we go. We've got our oxygen floating away. We've got our molten aluminium down here, so settling at the bottom. And it can be emptied through this little hatch down here, right? So we can get it out of there. Now, I did say you've got this oxygen forming around this here, your positive electrode. And what happens is the anode is made from carbon. And then when oxygen is formed there, it's at a really, really high temperature. And at these high temperatures, the anode is actually going to react with that oxygen. And when they react, what does it form? It forms CO2 gas. So if you think about it, if that anode is constantly reacting with the oxygen that's forming there, it's going to need to be replaced because it's going to get worn down. So that's another sort of downside to this process. You've got to replace those anodes all the time because they're being worn away. And so that's obviously a little bit costly. Okay, so this process in general, it gives us aluminium, which is great, but it does require still, a large amount of energy, and it's obviously quite costly to get things up to temperatures, around 800 degrees anyway, and you'd need to go and replace these cathodes and stuff as well, which is going to be quite expensive. So there it is. There's a brief look over the electrolysis of aluminium. Hope you've understood, how we get aluminium from aluminium oxide. Remember those little equations, and remember that the oxygen that's formed, because it's at high temperatures, is going to react with that electrode. to form carbon dioxide. There it is. Lovely. So that's electrolysis covered. Hopefully you've understood a fair bit more than you did before. And until next time, keep practicing your chemistry. I'll catch you again very soon.